So that's another key enabler, because it's one thing to deploy sensors and actuators willy-nilly, but it's another thing to actually be able to collect data from these sensors as well as send signals to these actuators in order to control the infrastructure, right? So that's grown through both your structured communication infrastructure, such as the cellular networks, and also ad hoc networks, right? So there are multiple low power sort of ad hoc network standards, 6LoWPAN being one of these. There are also sort of more long range sort of sensing capabilities like LoRa that's out there. So there's been a lot of evolution in both ad hoc as well as structured networks over the last many years that have made a communication fabric something that you can take for granted. Right? So these are sort of two key enablers. Uh, and now the question becomes, okay, once you have sensing and once you have communication, you're able to collect data about the environment, you're able to send signals. Now, what can you use this for, right? And that's where the sort of interesting use cases come in. And one key use case is one of sort of smart cities and smarter services for the public at large, right? You could, so we have this smart city mission within India where 100 plus cities are being upgraded to smart cities. Again, the definition of smart cities itself is very fungible. It's not like a single set definition, but the idea is that you want to give better citizen services for various public utilities and improve your livability of urban spaces. Right? So you want transparency in the services, you want accountability, you want reliability, and so on. Right? And all of this is sort of achievable. And one of the key means to achieve this is by having these information-driven decision making. Right. So right from the top down, right from planning city infrastructure to operating it on a daily basis, right? This has to be driven by sort of concrete data and concrete analysis, right? It can't just be based on, okay, I've been doing this in the past, let me continue to do that, right? Because the city itself is a organic entity, right? It keeps changing, keeps evolving, and so the system has to respond to that, right? And the ability to sense the infrastructure, right? Both the infrastructure as well as the sort of the social system, right? The human system that makes use of these services, right? Both of these are important in order to make decisions, right? So and then the actual analytics themselves are important as well. How do you use this information to take the right decision to achieve specific goals that you might have for the services that you want to render to your residents of your city, right? That's important as well, right? That's where this notion of a sort of closed loop cycle comes in within Internet of Things, right? Because at the end of the day, there are many ingredients to IoT, right? And you can sort of claim that many things are IoT applications. But for me, unless you have this kind of a feedback loop where you observe the system, you orient yourself based on the observation, you take certain decisions to achieve certain goals, and then you enact these decisions onto the system all over again, and then go back to your observation cycles. Right? This observe, orient, decide, act, right? This kind of a loop is what is distinct for IoT application, right? And as you'll see in many of the case studies we'll go through, this will be a first class entity that you can observe, right, as part of this, right? And again, just to sort of tie this in specifically, observation has to do with the sensing part as well as sort of the communication part to collect the data. Your orientation and decision making have to do with the computation and the analytics part, right, of the decision making. And the act part is again the communication and the actuation of the physical system. Right? So the top two have to do with sensing, actuation, and communication, and the bottom two have to do with computing and analytics. Right? So whenever you come across an IoT application, ask yourself, does this kind of a closed loop cycle come to play over there? So tying in this OODA loop with the sort of decision, specifically the decision-making part of this OODA loop, there you have to be able to manage and analyze large-scale data, right? Because you're potentially talking about not just hundreds, but potentially thousands or even millions of sensing sort of sensors out there, sensing capability that you have. So you want to be able to access this data at large scale, and you have to be able to sort of process this data often in real time rapidly, right? Because the whole idea of this closed loop cycle is that you want to take immediate action. It's not like you collect data for several months and then you sort of decide to take an action. There are certain decisions that can, for example, planning a deployment, right, or planning an upgrade to some infrastructure within the city. Those could be over months or over years of data that you've collected. But from an operational perspective, many of the decision making have to happen anywhere from the order of milliseconds to order of seconds or minutes, right? And these have to respond to the current state of the system as you have sensed the system, right? So there's a need to operate at large scale data as well as with low latency. That typically ends up being a feature of the operational aspect of IoT applications. And here you will you will need big data platforms and advanced analytics in order to help with the orientation and decision making process, right? So here again is a happy coincidence, in the sense that big data platforms themselves have evolved in the last decade or so. Be it NoSQL databases, be it platforms like Spark and Hadoop and so on, they have evolved. Likewise, we've seen rapid advances in machine learning as well, the analytics side of things, right? So that again all contributes to your ability to manifest IoT application in the real world, right? And tied to that is your ability to compute at scale as well, right? And here cloud computing is a key enabler, right? So you have these massive cloud data centers with thousands of servers within them that are virtualized, and you can literally go and rent virtual machines from the cloud within the matter of a few minutes. Within a few minutes, you can have tens or even hundreds of machines that you have rented out for the order of about a couple of rupees per minute, right? Or barely even less than a rupee per minute. You can actually rent virtual machines on the cloud. So even if you use those machines for even an hour or so, you're not going to pay more than a couple of hundred rupees, right? So contrast that with if you really had to purchase 100 machines, you'd be paying sort of lakhs, if not crores of rupees. Doesn't matter whether you use it for a few minutes or for a few years, right? But that's a very big transformation that's happened in terms of being an enabler for doing computation and analytics at scale without upfront investment in large computing horsepower, right? And most of you, if whether you realize it or not, have already been using the cloud day in, day out as part of your smartphone apps. You're using the cloud as part of your web portals that you access, e-commerce portals. All of them use the cloud, right? So pretty much any application that's been developed on the web in the last several years is hosted on the cloud. And likewise, a lot of IoT applications themselves will be hosting their so the brains of the IoT application tend to be hosted on the cloud, along with the data that's collected from the IoT application also typically tends to be hosted on the cloud. Right? So that's yet another enabling pillar. So communication, fabric, affordable sensing and actuation, advances in big data platform and analytics, and affordable computing through the cloud are the sort of the key ingredients to achieving IoT applications, right? And lastly, uh, more recently, you also started seeing edge computing as a first-class entity, right? And here, an edge computing device could be anywhere from an Arduino or a Raspberry Pi computer to even something like a sort of NVIDIA Jetson board with low-end GPU cards present within them, right? So the idea over here is that as part of deploying your sensing infrastructure, right, you oftentimes need some kind of a low-end computing power available within the sort of your physical infrastructure, right? And since devices like Raspberry Pi tend to be fairly cheap, these cost about maybe 5,000 rupees or so, and these could be used for, let's say, managing or collecting data from tens or maybe even 100 sensors or so out there on the field. And then typically these tend to sort of accumulate data from these devices and push them off to the cloud, right? But as you have potentially hundreds or thousands of these edge devices deployed on the field, one of the questions that to ask is, can you put them to better use than just shoveling data from the sensors to the cloud, or just forwarding actuation signals from the cloud onto the actuation devices, right? So there is a lot of interesting research to be done in the context of using these edge platforms for doing some of the analytics that you would be doing in the cloud, or even doing some of the data management that you would be doing in the cloud, right? So that again is an opportunity that you have through the use of edge devices. And similarly, you have cloud devices as well, with which can end up doing even sort of machine learning or inferencing using uh, low-end GPU cards that are available, right? So the computing spectrum itself ranges everywhere from the cloud to the fog to the edge, and each one has their different trade-offs in terms of latency for accessing access to the data, the computing power that they have, reliability, and so on. Those are variable, and sort of depending on the IoT application, you can sort of make use of them in an intelligent manner. But again, I won't get too much into this because there's a lecture, I believe, coming up tomorrow on edge, fog, and cloud. So you'll learn much more about these. But it's useful to keep in mind this entire ecosystem that's available, right? Which helps achieve IoT applications. And you'll see flavors of all of these in the various case studies as well, right? So what we'll do over the rest of today's lecture, right, is go through multiple case studies, and for each of them, I'd like to highlight the specific sort of problem being solved, the social problem being solved, and potentially some of the technical problems being solved. What are the specific technologies that were used in these IoT applications, and how these technologies were integrated together, right, to sort of give you a holistic solution, right? And also briefly talk about how do you validate the solution, how do you know that what you are getting is correct, and what are some of the research challenges that we encountered and we overcame as part of this, and also what are the gaps and limitations, as in no solution is perfect, nothing is going to give you all that you want. So being aware of what you are able to solve successfully, as well as what you are unable to solve successfully, either because it needs more research or there are certain inherent infrastructure limitations that prevent you from doing that. These are good to understand as well. So we'll try to sort of get a flavor of all of these in the different applications that we go through. And specifically, the sort of application themes that we'll talk about are bulk of it is going to be around smart city based applications. There I'll walk you through case studies on smart power grids, doing demand response optimization, smart power grids, having sort of equitable and safe water distribution networks, as well as low cost urban air quality monitoring. And these are all sort of projects that I've been involved in the last decade or so. And likewise, as Meenakshi mentioned, we will also talk about smart health in the context of mobile app-based COVID-19 contact tracing app that we've been we put together in the last year or so. It's deployed at 3 different universities in India and so on. So we'll talk about that as an example of IoT for smart healthcare. And lastly, we'll talk about some of our ongoing research in the area of smart mobility in the context of drones as an autonomous platform. So that's going to be the sort of sequence of case studies. Before I jump into the first case study, let me pause for a moment, see if there are specific questions that you have from what we've covered so far, and then we'll take it forward. So if you have a question, feel free to unmute yourself and ask a question.
Yes.
Aditi this side. So I had a question on the challenges part that we discussed some time back on IoT as a big data challenge. So one side of the challenge is about the data itself, that is, processing the data or get a huge amount of data. So I work on the application side of IoT. I work on projects related to smart cities. So we take up projects on water management systems, parking management systems, transport management. One major challenge that we face is in the sensors itself, as in the accuracy of the data that we get decides on how efficient our system is built. So is this challenge addressable, or is it a limitation of IoT that you will have to rely on sensors and their accuracy? Because some point it might be saturated that a device can give you only this much of data and you work with it. Or is it possible to make the devices better?
Right. No, that's a great question, and we'll specifically I'll talk about one of the challenges in the context of this air quality monitoring using low cost sensors, where the accuracy of the sensor is one of the key challenges that we uh, address and continue to address as part of the problem. But again, it all depends, I would say, on the cost of your solution and the accuracy that's required, right? Because oftentimes, for example, if you take something like uh, smart metering of utilities like power meters and water meters, right? So the bulk of the instrumentation cost is anyway paid by a dumb meter as well, and it's just a question of adding some additional capability to the dumb meter to give you real-time monitoring capabilities, right? So there the loss in accuracy might not be a lot. It might be good enough for the application that you have in mind. But then if you have sort of situations where you want to deploy low cost sensing and still try to achieve certain degrees of accuracy, there again the question becomes what are the use cases and how much accuracy is good enough, right? Because uh, we want to sort of take certain sort of mission critical or things that have to do with life and death, their accuracy required might be much higher. But it's for broad policy making, lower accuracy might be adequate. And there again, the question is how much of accuracy can be enhanced using data analytics technique, which is one of the directions that we took in this air quality monitoring projects, which I'll talk about as well. I don't know if that helps answer, but it's essentially it's a tough problem. Yeah.
Yes. Okay. Sure.
Somebody else also started along with Adhavi?
Sir,
Yes, Divyadarshi.
sir, can you give me an idea about your fog computing? Is it the same as cloud computing or something different?
Sure. So I'll briefly talk about that, but you do have a whole session tomorrow on fog computing. Right. One way to think about fog is, so if you look at the properties of edge computing, the edge devices are typically alongside the sensors themselves, and these sensors themselves are literally physically monitoring some sort of infrastructure. Like it could be a traffic camera, it could be a temperature sensor, it could be a water meter, and so on. Fog computing is uh, something that is still close to the edge from a network topology perspective, right? So if you think of a cloud data center, right, a cloud data center might be hundreds or thousands of kilometers away from where the physical devices are present, right? Because typically you might have just a few cloud data centers for the entire country, right? Likewise, the edge devices are typically alongside the sensors, right? Now, one of the challenges with edge devices is that they are constrained devices. So they're compute constrained, they're memory constrained, they are sort of even from a reliability perspective, they are not very reliable because they're out there on the field, and they could get affected because of rain and sort of ambient temperature and so on, right? So edge has some limitations. Now, fog computing can potentially be introduced as an optional layer. So you might have maybe more higher end computers like workstation level computers or a small even cluster of these workstations or even low end GPUs that are present at the city level, right? It might be you might have one or a few per city, or you might even have one per neighborhood, right? And what they could do is that they could offload some of the computing or the storage or the analytics aspects that cannot be achieved at the edge, right? But maybe it is not prudent to do it on the cloud either, partly because maybe there's a lot of bandwidth that you have to expend in moving the data. For example, if you're looking at video data, right, from let's say a traffic camera network, right, moving all the data to some sort of national level cloud data center is going to consume a lot of bandwidth, right? So there it might actually make sense to have more of these sort of workstation class devices that are there within the city, so the bandwidth is sort of kept within the city, doesn't hit the core internet network. Uh, but there again, the role of cloud fog is sort of selective. Not every application might benefit from the fog. So that remains to be seen. The other thing I also want to sort of caution, and again, this might be reiterated in tomorrow's lecture, is sometimes the definition of fog and edge are a little bit imprecise, right? So you might have some domains that call a fog as an edge device, right? Others that might sort of call an edge as something on the embedded platform on the sensor directly itself, right? So the wide variety of opinions in terms of what's a fog versus what's an edge. So you have to be careful about that. But to me, one potential manifestation of the fog is through the 5G base stations that might be coming along in the next few years. And there, these base stations will have computing available alongside these cell phone towers. And the design of 5G is such that you can actually make use of this computing through the communication pipeline, right? Because till 4G, you couldn't actually do that. There's a clear separation between the communication layer and the computation layer. But with 5G, you can actually blend the two together. So as these 5G base stations come along, I think of these as fogs. The telco providers themselves might think of these as the edge. So that again is another way you can sort of tap into edge/fog.
Okay, sir. Thank you, sir.
Sure. Any other questions or comments before we move along? Okay, great. So let's go on ahead to the first case study. And that has to do with how do you sort of make a smart power grid. How do you design a smart power grid, right? How can you make your power grid smarter, right? And this is actually work. It's probably close to 10 years right now. Back, this is my first brush with IoT and cyber physical systems. But some of the ideas from back then are still relevant, right? And it might be, you might also notice how the technology itself has evolved over the last decade or so, based on some of these early ideas around IoT, right? So this is actually work that I did at the University of Southern California before I returned back to IISc with my collaborator Victor Prasanna over there, and there were several others from UCLA and other places as well. And this project was done in the context of the city of Los Angeles, their power grid, right? And back then, sort of the smart grids were still a new concept. People are just trying to get a hold of what smart cities and IoT and so on were. And one of the key aspects is that within a smart grid, you have a lot of sensing and actuation capabilities, right? And this might range everywhere from sensing the sort of power consumption for an entire building or a residence as a whole, to more fine-grained sensing of individual rooms or individual equipment within a building or a home, to more at the gross level sensing of your entire distribution and transmission network, these long distance networks that you have, right? So the sensing can happen at various granularities, right? From the entire sort of long distance transmission to neighborhoods like the transformers and so on, to individual houses, to individual appliances within the houses, right? And some of this sensing becomes, smart grid has multiple sort of necessities, right? So one of the key being that you want to be able to have an efficient and reliable power grid. So you want to make sure that the available power capacity is well distributed so that everyone is happy, you don't have a lot of power failures and so on. And the other challenge also comes in from the fact that you have a lot of renewable power come into play, like solar and wind power. And one of the key challenges of such renewables, many of such renewables, is that they are unreliable because they rely on the day being sunny as opposed to cloudy, or the wind blowing adequately and so on, right? So as a consequence of this, unlike your traditional coal or gas powered power plants or even nuclear power plants, where the supply is more reliable, right? Unless there's an equipment failure, the supply is more reliable. And only the demand might fluctuate from within the residents of the city. With renewables, even the supply is a little bit unreliable, right? So then you need means to accommodate such unreliability, right? And that's where one of the key questions for such the smartness in the power grid comes in. Under such a dynamic situation, can you make use of information that you collect, that you sense about the power grid, to better manage the distribution of the power within the city, right? And this project was done in the context of the Los Angeles city, which is one of the largest utility within the United States, having over nearly 4 million residents. and the city of LA consumes 1% of the entire power of the United States, right? So it's a big power hog over there. So obviously, some of the validation that we have to do we are able to would have a big impact, right? If we're able to demonstrate it on such a big city, right? So here again, these are the three different layers that you can think of. One is the entire power grid, long distance transmission, and then the distribution within your city, right? So the transformers and substations and so on. And then even within a building, right? So within a campus or a building, you can have fine-grained controls, right? So many of the newer buildings that you'll see, whether in India or abroad, they'll actually have fairly sophisticated sort of building area building management systems, right? So where there'll be a control center where you can observe the power consumption of every air conditioning unit, centralized air conditioning unit, or every building that you might have, or even the power consumption by your elevators and so on. All of these can be centrally observed, and some of these can actually be centrally controlled as well, right? So if you wanted to, the sort of control center of the building can actually, let's say, if you've got two elevators in a building, you can switch off one of the elevators, right, to conserve power in case at nights you're not going to have a lot of traffic, right? So there are a lot of campus or building level controls that are available nowadays in most modern buildings, right? So the question is, can you make use of such ability to take more intelligent decisions, right? And one of the sort of canonical use cases that we were trying to solve within a smart power grid was something called demand response optimization. And here the idea is that, can you shed, shift, or shape the amount of power consumed by residents of the city, right, in real time, based on the current situation for the power grid, right? So here again, tying this to the renewable use case, right? So let's say today, meaning in Bangalore, looking out of the window, it's a cloudy day, right? So if the Bangalore city were being supplied by a lot of solar power, right, I would know that the supply of solar power is going to reduce today, right? So which means that I cannot have all my consumers consume power at their normal level, because that's going to cause, because I don't have enough power available, right? So one thing that we typically do within India is that you essentially have this load shedding, right? So sometimes this is planned, sometimes it's unplanned, right? Suddenly in the middle of a day, power might go out for an hour or two, right? And this is one way of doing it where the consumer doesn't have a say in the matter, right? So they're essentially told you don't have power because we don't have enough supply coming in today, right? But a more intelligent way of doing it is to literally ask consumers, right? And again, not ask manually, but ask in an automated manner, right? Today we have less power available, power supply available. Would you be willing to reduce your power consumption? And in return for that, we'll give you some kind of an incentive. We'll give you some kind of a discount in your monthly bill, right? So that is a much more probably a fairer way of doing it, where everyone is happy, right? So no one has to sort of deal with unwanted power outage, right? So just to sort of give you an illustration of this, let's say these are 24 hours in a single day, right? And what you have is the amount of power that's normally consumed. Let's say this red line refers to the normal load on the power grid, right? And typically at nights and early mornings, it's going to be low. It's going to potentially peak in the middle of the day when everyone's in their offices, all the central ACs are running at full load and so on. And it might sort of plateau out or flatten out towards the evening, right? So this is just, it might be different for different cities, but this might be how it looks like, right? Now, when you talk about demand response, we are trying to see if we can shape this curve to look slightly different, right? So that maybe you reduce your peak load, right? Because if you think about it, power grid has to provision for the peak load, right? So if your peak load is a certain number of megawatts, you should make sure that you have enough power to supply at the peak load, right? So by shifting down your peak load, you can actually ensure that you can have less provisioned capacity, or you can sort of make do with renewables, which might not give you the full capacity at any given point in time, right? So when we talk about shedding, you're saying that you're eliminating the power usage for a certain period of time. When you talk about shifting, we are saying that we are shifting it maybe from the afternoons to the evenings. You're shifting it from, let's say, a peak load period to the early mornings or late evenings, right, where the demand is lower, right? So it's less about how much cumulative power is used and more about how this power usage is distributed through the entire day, right? So for a utility, the ideal scenario is a flat line, right? So if it's a flat line, it means that they just need to keep supplying power at a constant rate and the demand is at a constant rate, right? But unfortunately, in real life, that's not how it is, right? So that's what demand response optimization is. So the question is, how do you ensure that the customers can shed or shape their demand in response to requests by the utility, right? Yeah, these are examples of, again, from within Los Angeles. 1 to 4 was the peak demand, 10 to 2 and 5 to 7 were the medium demand, and the base load was between 8 p.m. and 9 a.m., right? So that's where the base load is there, right? So the question is, can you do that? So do you want to shift or do you want to shed, right? So shift, this is an example of shifting. The orange line is you're shifting the load slightly differently. Shedding means you're actually reducing the load of the peak, right? So a couple of questions that arise over here. So when we talk about demand response observations, one question is, when do you initiate such requests, right? So you have long-term planning for a utility where you want to say, hey, in 5 years time or 10 years time, how much load will Bangalore city need, right? And based on that, I have to start planning my sort of power generation stations and so on, be it solar power or wind power or so on. So those take tens of years to plan ahead and enact, right? But what we are talking about is sort of real time, within a single day. Can you plan ahead by a few hours and so on, right? That's where the demand response optimization comes in, right? And things like day ahead and so on, even within India, nowadays you have this energy market. So if, for example, if you know that your demand tomorrow is going to be so and so, and maybe you have one of your supply stations that's going to go down for maintenance, there are actually these spot markets, because India has a fairly reasonable way of actually moving power from even one state to another state through our national grid network. So you can actually even, let's say, lease power from a different city or a state ahead of time, right? So through spot markets and so on, right? So things like day ahead or month ahead, you can actually plan through this energy markets. But on that particular day, if there are sort of shifts in the demand or supply, you want to be able to respond to that, right? That's where the DR comes into play, right? So here, some of the key questions to answer is, when do you start your demand response? What's the duration for your demand response? And how much of shifting of load do you want, right? So once you have an estimate of this, then the question is, whom do you talk to in order to sort of request this reduction? And what strategy do those entities put into play to achieve this reduction, right? And one other sort of interesting side note over here is that in any city, right, the residential power consumption is only a sort of typically a minor fraction of the overall power consumption, right? A large fraction of the power consumption is typically by your industries and your factories and by your software technology parks and so on, right? So those actually consume more power compared to residents, right? So in order to actually achieve something like demand response, you want to target your large power consumers, right? Such as your, let's say, if you got a software park, right? So and these large consumers also tend to have more of these sophisticated building management systems deployed over there, right? So those would be your pool of customers whom you would go and talk to, right? And effectively, another way of thinking about it is that these large customers already have an IoT solution deployed internally, right, from various vendors, right, as part of their building management system, right? So now, can the power grid IoT system for the city talk to the building IoT, building level or a campus level IoT system automatically in order to achieve this demand response, right? That's sort of the big picture of how to think about it, right? Right. So let's see how some of these sort of, now, hopefully the goal over here is clear in what we want to achieve for demand response optimization from a smart power grid. Let's see how some of this is achieved. Right? So the validation that we did was at the University of Southern California campus, which is one of the largest consumers of power in the city, right? So you can think of it as any large university campus. It had about 150 odd buildings in 2 sites within the city, with more than 50,000 people. That it's a mini town by itself, right? So you got hotels, restaurants, dorms, residential buildings, sort of academic buildings, office buildings, so on, right? That's a mini township, right? And the USC campus itself was fairly instrumented through building area networks from Honeywell and so on, right? So you could actually go and look at a control panel within this energy management center, and that would actually tell you literally at each room level, it would tell you how much of the cooling is happening within that room. From AHUs are essentially your centralized AC units. So how much of what's the temperature in different rooms based on the thermostat, what's the current amount of volume of cold air that's being supplied, and so on. So that can actually be observed in real time, right? And you can actually control these as well. You can actually choose to, let's say, switch off an AC in a particular room, right? Or increase the volume of air in a different room, and so on. Right? So there are thousands of these sensors deployed at the level of each equipment and each room and so on within the entire campus, right? That allow you to observe the entire campus, right? And you also have potentially hundreds of these actuation units, which you can control at the level of an elevator or the level of let's say floor lighting, or at the level of a centralized AC and so on, right? So all these things are possible, right? Now, given this, what we did was put together a IoT sort of pipeline, right? That taps into all these pieces together, right? So let me sort of start off. One is the building management system that we tap into, and you also have the facility management, that is centralized unit, and then you also have the environmental factors, such as what's the temperature and sort of what's the ambient situation, what's the campus calendar, is it summer, is it sort of regular academic semester, and so on, right? All these things come into play as part of collecting your information, right? So the first part is to actually monitor both using physical telemetry sensors as well as virtual ones, like campus calendar, right? It's sort of a piece of information that's available. You can scrape a website and figure out what classes are scheduled in what rooms, right? That actually gives you and what are the number of students who are enrolled in a particular class, right? So these pieces of information actually tell you what the power demand might be in a particular classroom at a particular time of the day, right? So these are pieces of information that you can sort of get from the social and academic calendar, while you actually get the information of the physical environment from the IoT network as well, right? But all of these are ingested together. And back then we were using a cloud-based solution, so all the data goes into the cloud, where you sort of store and sort of disseminate data, do some visualization, and so on as well. But then one of the key, there are 2 key analytics that we were performing as part of this, right? So one was, can we do demand forecasting for different buildings on the campus, right? So can we get a sense of what's the load going to be, right? So because again, if it's a cloudy day, right, maybe the AC is not going to be working at full speed, right? So the demand is going to be lower. If it's a weekend, obviously the load is going to be lower, right? If it's a summer break as opposed to a regular semester, the demand is going to be lower, right? So can you use these various factors that you have available to forecast the demand at, let's say, for every building on campus? And we had about 100 or so buildings that we were observing in one of the 2 campuses at USC, right? So that's part 1, right? Because that gives you a sense of when you get a curtailment request, it tells you what's the demand going to be, and you can sort of look for the opportunities where the most curtailment can take place, right? The second part comes in terms of when you get a request from the city, right? And the city says, hey, today the winds are not blowing as fast, so our solar, like wind power generation, has dropped by so and so factor. The overall supply to the city has gone down by 5%, right? Between for the next 3 hours, right? Now the city might come in and say that, hey, how much reduction can you give me, right? And it might send a signal automatically to every large consumer of power within the city, right? Now, when a campus like USC receives such a request, right? Again, all of this is automated through IoT-based communication channels, right? Can you actually automatically use information about your demand forecasting, as well as various strategies that you might have for reducing the power usage, and we'll talk about some of those. And can you actually use that to enact this kind of a reduction automatically, right? So that you try and meet the target given to you by the city for reducing your power usage, right? That really is what we were trying to do. So how do you do good demand forecasting? How do you do good curtailment strategies, to meet reduction? Right? So, all right, some animations. All right. So here, I'll talk about two sort of technical challenges that we addressed as part of this big picture goal, right? So one was in using real-time data from the various sensors deployed on campus to do good demand forecasting, right? And here, when you're looking at potentially thousands of these sensors, right, which are generating data in real time, potentially every minute or every 15 minutes and so on, you need to have a way to continuously consume the data and continuously analyze the data, right? So this this rate at which you get the data itself might vary over time. The sampling rate might not be constant for every instrument. Not every instrument might be reporting data 24/7. The size of the events from different instruments might be different, right? So when you look at it from a big data platform perspective that's running in the cloud, it is going to be receiving a lot of event streams, right? And it has to adapt to the rate at which it's receiving data in order to ensure that certain latency guarantees are met, right? So you might have a sort of requirement that any event that you receive should be processed within 15 seconds, right? And you should be able to analyze that within 15 seconds. It should be stored within 15 seconds or so, right? Since the data rate itself is varying, right? Here you need to be able to make use of some of the elastic capabilities of the cloud, right? Again, one of the benefits of cloud computing, right, and maybe you'll go through this in more detail tomorrow, is that you can instantaneously spin up and spin down virtual machines, right? So you can literally send a signal to the cloud provider saying that, hey, give me 2 new virtual machines, right? And in the matter of a couple of minutes, you'll have 2 new virtual machines available to you, right? And then you can sort of run, let's say, another copy of your big data platform, right? Likewise, if your load is low, right, if your data rate has fallen down, you can immediately look at the set of virtual machines you already have available, and you can decide to retire a couple of them. You can tell the cloud provider, hey, I don't need, let's say, these 3 virtual machines because my demand is low. You can take it back, right? So this can happen within the order of a few minutes, right? And you only pay for what you use. If you rent a VM, you pay for it. If you release the VM, you don't pay for it, right? So the question is, can you modify a big data platform to automatically be responsive to the data rate? That was something that we did as part of a stream processing system that we built in-house called Flow. And there, the idea was to actually allow, so as you have a set of events come through from various sensors into the cloud, you want to be able to pre-process them. You want to be able to maybe do some data transformation. You want to do some normalization, maybe some interpolation for missing data and so on, right? And then maybe you want to store it or do some analysis or do some sort of trending and prediction of load and so on, right? So for example, this could be the current load on the system, current kilowatt hour consumption from various buildings could be coming in this event stream, right? And you might be using some kind of, let's say, a time series modeling, right? Like an ARIMA model or something like that, to look at the current series of events you've seen and use that to predict the next 1 hour or 2 hours of demand that you might have from a power consumption perspective, right? So one of the key aspects that we looked at over here is that based on the incoming rate, can you do intelligent scale out and scale in as the sort of maybe the capacity of a particular, let's say, process running within a virtual machine might be to handle, let's say, 1,000 events per second, right? And as you start saturating the capacity, maybe you want to spin up another process, right? And if the capacity of a virtual machine itself is exhausted, you might want to spin up another virtual machine and spin up an extra process on that, right? So you want to keep track of the rate at which the input is coming in. You also want to keep track of the latency that you are taking in order to complete your processing and analysis, right? And using these two metrics, you want to dynamically sort of scale out and scale in the number of virtual machines. So that's something that we worked on, and we were able to demonstrate that we can sort of adapt our to that.
So here, when we talk about the sensors, are we talking about the sensors that are in the campus that we are trying to control or get data from? Or are we talking about the centralized system, that IoT that is there in the campus that we are interacting with?
Okay, so in this particular case, these were the sensors which were on campus, right? And would be transmitting the data to the cloud. for centralized analysis.
Okay. So, I mean, what is the difference between directly talking to the sensors and talking to the IoT system? Because the campuses generally have their own IoT systems that does the computing, does the analysis for their internal purposes, right? So, why would it not be efficient to talk to the IoT system on the whole and not the sensors? I mean, what is the difference in making?
All right, so maybe I should have been a bit more careful about my response. So when we talk about, when I say we get the data from the sensor, we get the data from the sensors to the APIs exposed by the IoT system, right? So that's the right way to put it. And one of the sort of reason why we don't just use the IoT system to do the processing is many of these are proprietary systems, right? And they charge an arm and a leg to add any kind of software feature, right, into that particular system, right? Meaning, of course, things are changing nowadays, but back then it used to be you used to have some very proprietary protocols also that you had to talk to. But by actually extracting the data out into a cloud-based system where you manage the data, you analyze the data, it gives you way more flexibility in terms of what analysis you can do. So you literally think of the IoT system, building area network, right? That's provided just as an API for exposing the sensors and exposing the actuators as well.
So, it is a decision between flexibility and latency.
Right, you can think of it in that way, but even it's mostly a question of cost versus cost and flexibility, right? Of what you can do using the proprietary solution. Right? But the latency part is something, back then we were using a cloud-based system, but the more recent work that we have done is more on edge-based system where even the latency is less of a concern, and that's sort of being mitigated as well. Right? Great, but good question. Thanks for that. Yeah. All right. So just to sort of give an example of how we sort of one of these scenarios where we responded to the variability in input rate. So what you see over here is a pellet is like a unit of computing that we can spin up. So as you see the number of events, input rate, that keeps increasing, you also see that the number of processing units that you allocate is also increasing. And what you see in the green is the latency. So whenever the latency starts exceeding a certain set threshold, you start increasing the number of processing units, number of threads or processing units. And if that exceeds the capacity of a VM, you also increase the number of VMs themselves. Right? The orange lines is the number of cores or number of VMs. The brown lines are the number of threads or number of processes. Right? And the blue lines are the latency that you achieve. Right? As you can see, the moment you start exceeding a certain threshold, you start responding automatically, and you start bringing back the latency within a manageable level over here, right? And that helps you adapt dynamically, right? And likewise, if your input rate reduces, your number of scale out that you do for your threads and for your VMs also reduce, right? So this is about ensuring that you get the appropriate set of performance for, and you only pay for what you really need, right? You don't over provision or under provision the computing units, right? And sort of get the you achieve quality of service for a affordable cost on the cloud. Right? There's an example of that. The other sort of aspect that we also looked into was in terms of doing modeling of the demand itself. And what you see over here are sort of figures within 24 hours on different days of the year for different types of buildings within campus. So within an office building, you'll actually see that between 9 to 5, you actually see a lot of energy consumption, right? And during the off hours, the consumption is lower, right? You also see that for weekends, the consumption is low, even during the sort of regular 95 hours, while for weekdays it's higher, right? On the other hand, if you look at a hostel building, right, a dorm building, right, there the sort of consumption is sort of very different pattern, right? So until about maybe kids are pretty active all the way till probably 2 a.m. or 3 a.m. In the morning, and maybe there's a few hours of sleep, and then back to sort of doing your homework and classes and all those things, right? So there again, it's a very different pattern, right? So one of the questions is how can you do sort of reliable prediction of some of these demand patterns on different types of buildings? And this also happens for different buildings within the city itself, right? So we have some data from there also, and here again the variability is fairly large, right? And here we have looked at meaning a lot of these are plugged in. You can think of these algorithms or analytics as being plugged into the stream processing system that we saw earlier on, right? So the logic that runs within the stream processing system could very well be a prediction model, right? So over here we are looking at it from a system perspective, but you will also have to look at it from an analytics perspective. Can you give an accurate enough prediction so that you know what's the demand going to be, and in turn you can sort of respond to curtailment requests, right? So here we looked at back then at different types of time series and ARIMA models for doing such predictions. So ARIMA time series is a univariate prediction. You only sort of need historic data about just the time point and the sensor observation, and use that for forward prediction. And it can sort of capture both seasonality, both daily trends and monthly trends, and so on. Right? But it can only work over recent data. It doesn't do sort of long-term prediction. It can only do short-term prediction. Right? You also have feature-based multivariate prediction models such as regression tree, random forest, and a bunch of other things. Back then we were playing around with random forest. So here you need a lot more features, but you can actually be more robust to predictions across a longer period of time, not just short-term predictions. Right? So we've looked at multiple of these models for doing demand prediction. So I won't get into details of that. This is just a high-level brushstroke, what you can potentially do as on top of your real-time data streams that you receive. And now once you have...
In your particular application, which one turned out to be more efficient? Is it the data-driven model or the time?
Right. So the ARIMA models were pretty good for coarser granularity, right? So if you were doing, for example, for campus level or even for large buildings, we were able to get something like 90% or so accuracy, right? At 15-minute granularity, right? But the moment you start getting into more smaller buildings which have lower load, right? ARIMA wasn't really good, and ARIMA wasn't good for long term, like 2 days in advance, 3 days in advance. So there, the regression-based models were a bit more robust, right? So it's not like one size fits all. Depending on the scenario, different models come into play. In fact,
smaller the size, the data-driven works better.
Right, because they are more sensitive. Because for small buildings, there could be very localized effects which cannot be captured properly by the ARIMA-based models, right? So we saw that for larger buildings, ARIMA was good, but for smaller ones, regression was good.
Also, what is the gap they signify in the first building that you showed, sir? You showed a dormitory building and an office building. Yeah. So the dorm building has more of a distributed, there is no specific pattern in the peak hour. If you see in the office building, I see a gap between the green lines and the blue lines, a significant gap. So does it signify anything? Or?
Well, it's students versus staff, right? That's what it signifies. Right? So students are active all times of the day, right? In a dorm, right? There is a pattern for them. While office goers in administrative buildings, right? So like a finance department or HR building, right? So they have set timings, right? So that's what this reflects. Right?
Okay.
Yeah. So that's where the social aspects comes into play as well, right? So knowing that a building is a dorm building, right, might actually help tune your model better compared to knowing it's an office building. Right?
So the customer base also is a factor for deciding the kind of.
Yeah. In fact, if you look at, let's say, a teaching building, right, like lecture hall or something like that, that would actually have a very different patterns. There you might actually see spikes when classes are happening, and when classes are not happening, it will actually go to zero.
Yeah. And there it will be distributed because the teacher and the students will be active at the same time.
Correct. Yes.
Okay.
So these are factors that come into play as well. That's why it's not just looking at sensor-based data. It's also looking at class schedules and so on as well that are useful in this context.
Okay.
And just sort of there are several papers. Maybe I should put a note to some of these papers in my slides. There are a bunch of papers, research papers that talk about these in much more detail. I'll refer you all to that later on. So maybe during the lunch break, I can add references to those papers. So you can sort of read those up for much more excruciating detail, or sort of drop me a note separately as well, and we can take those up. All right. So we've so far seen about how some of the software systems work, the end-to-end system components are, how you do sort of prediction. And now let's get to the curtailment part, right? So here again, there are two types of curtailment strategies. So one is direct control, which you do through your building control system. So for example, for air conditioning units, which have centralized control, or lighting units and elevators, you have direct control, right? And then you have a set of voluntary controls, because some buildings might not be fully instrumented. where you might have to sort of request users to, let's say, turn off their local AC unit, not a centralized AC unit, or sort of reduce the lighting and so on, or sort of power down some of their computers and such, right, which are not centrally controlled, right? So there are voluntary and sort of direct controls. Voluntary controls, again, there's a bunch of work that we did with some behavioral folks, behavioral psychologists at USC, to sort of look at different types of messaging, right? So that would sort of cause people to respond and reduce their power usage. But that's a whole different problem altogether. That's why the social aspect of things come into play. But the direct control is much more deterministic, right? So here you have the ability to change the temperature set point for different rooms. So if you want to reduce your energy usage, you can increase the AC temperature from, let's say, 25 degrees Celsius to 27 degrees Celsius. You can you can reduce the amount of volume of air that's, this is a fan speed setting, right? You can have a low speed, medium speed, high speed. You can change that. You can also do duty cycling. So for example, if there are 4 different AC units in a single floor, you can ensure that at a time only 3 of the 4 AC units are working, right? So after an hour, maybe you shift to a different 3, and after an hour you shift to a different 3. That's called duty cycling, right? So these are the different types of controls you have just on the AC unit. So here we actually did a bunch of field measurements and benchmarks on the effect of different strategies, right, on different buildings. So that gives you sort of a database of effectiveness of different control strategies, so that you can put them to play, a combination of them, whenever the time is appropriate. So now comes the question. So once you have this information on the current load on different buildings, as well as past experience on what the curtailment strategies on different buildings are going to get you in terms of reduction and load, now you actually have to intelligently combine the curtailment strategies to meet a certain goal that is given to you by the city. So you might come in and say, hey, give me a 500 kilowatt reduction in your load for the next 2 hours, right? Now you have to go and pick the right set of buildings that will just give you adequate. You don't want to exceed that 500 kilowatt, nor do you want to drop below that. You want to find the sweet spot, right? At the same time, you want to sort of have some reliability that you will actually achieve it. And you also want to ensure that you don't keep going to the same set of buildings every day and turning off their AC, because that's going to make people unhappy in those buildings, right? So there are a bunch of these social and optimization factors that come into play in order to choose a collection of buildings that will give you the right set of performance behavior. And this again gives you an example of what's the amount of fraction of buildings and curtailment strategies that give you different types of reductions on the x-axis, right? So this again can be designed as an optimization problem. So where you want, given a certain target and a time period, you want to mix various curtailment strategies such that the sum of all these curtailments is as close as possible to the required curtailment strategy, right? So and one of the ways to solve this problem is something that's a classic problem called change making or coin making. So if you're given a 100 rupee note, right, how do you split it into coins so that you have the fewest number of coins that give you exactly 100 rupees, right? So you can think of this 100 rupees as the total curtailment that you want to achieve, and all the coin denominations that you have as the curtailment you can achieve from each building, right? And you want to find a collection of these coins such that the total is exactly equal to your overall 100 rupees, right? And that's pretty much what we reduce this problem to. So so you do a change making problem, you have a greedy heuristic to solve that. So as and when you get a request from the sort of power grid utility, you sort of enact this. You look at the current demand for the predicted demand for various buildings, you look at the various curtailment strategies and how they would shape the demand, and then you pick the right set of curtailment strategies in order to achieve the and then you actually enact it. You sort of go to each building automatically through your building area network, and you sort of program them to sort of enact those strategies, right? And all of this was done within the USC test bed. And this gives you an example of what a real demonstration that we did of this particular strategy, where you actually get the event windows, a period for which you want to enact the demand response. This blue line is what would have happened if you hadn't done demand response for those periods. This is from 1 o'clock to 5 o'clock in the afternoon. And the orange line is what you actually managed to achieve, right, based on performing those curtailment strategies, right? So, and in one of the demonstrations, we are actually able to shave off almost like in one of the, this is not that demo, in one of the demos we actually shaved off about 5 megawatts of load from a campus that was consuming 25 megawatts. So we essentially reduced 20% of load on a campus, and 5 megawatt is a lot of energy. And that's something that we were able to sort of provide the city utility as a result of our curtailment strategies. Right? All right, to summarize, what are the key takeaways from here? So one is that this was an example of doing real-time analysis over IoT data streams on the cloud by leveraging cloud elasticity. We are also able to perform various types of real-time prediction on top of the IoT data we were collecting from the various sensors and other sources in order to do demand prediction. And we are also using various optimization strategies in order to select the right mix of curtailment strategies in order to do demand response optimization. And this was deployed on and demonstrated on the field as part of this particular project, with the USC campus being a test bed and the LA city being the utility provider. Right? All right, let me pause over here and see if there are any other questions before we go on to the next case study.
Sir,
Yes.
so you have said that two curtailment strategies are being followed, direct control and voluntary control. How effective is that voluntary control is a process, sir? Because all of the users can't reduce suddenly the power consumption when we ask. So how effective that is implemented?
Right. So voluntary control was a bit of a mixed bag, right? So the reason why we even tried voluntary control was that it's a loose proxy for residential houses within the city, right? Because residential houses typically don't tend to have some building area network or complex control systems, right? Nowadays, some of them do, right? But it's still rare, right? So which means that if you want residential units to reduce their consumption, right, you have to go for voluntary control, right? And like I said, maybe about 50% of the load might come from these large like consumers, 50% from the residents, right? So understanding how voluntary control works was helpful. I wouldn't necessarily say that we were able to get a lot of reduction from voluntary control, but the number of voluntary control sort of rooms or buildings within campus was much smaller than direct control, right? So in that sense, you'll have to multiply this voluntary control reduction by potentially 1 million residents within a city, right, to get some tangible returns. Right? So bottom line, we tried different messaging strategies. We got some reduction, but not as much as we got through direct control.
Okay, sir.
And also the other sort of caveat to note is that within sort of campus buildings, it's not like you have a lot of options for voluntary control. Lighting, you could do that. Maybe you open the curtains and sort of turn off the lights, but lights are a very small fraction, right? Within residential households, which there weren't many in USC campus, you could have things like your sort of washing machines and sort of things of that sort, right? That have much more load compared to just lights and so on, right? So that I would say is one of the limitations in being able to do voluntary control at scale, is still an open challenge.
Yes, sir. That's the difficulty facing in voluntary control, sir. That's
Right.
why I asked. Thank you, sir.
Yeah, and it's also a question of the incentives and so on, right? So one of the interesting things we did, working with our behavioral psychologist colleagues, right, was try to do different types of messaging, right? So one messaging was saying that it's as if it's an anthropomorphic view of the building, where the building says, hey, I'm a building and I want you to take better care of me, right? I'm feeling very cold today, so please keep me warm by increasing your AC temperature, right? In other strategy, we said that, hey, think about the future of your kids, right? Think about making the earth a green planet and all those things, right? So you only have one earth. So there are different types of messaging that were tried out just to see which ones will resonate with users. And the goal eventually was to sort of, if you have much more social information about the users, you might even sort of make targeted messaging, right? Just like Facebook and Google give you targeted advertisement. The question was, could you do targeted messaging for individual users to try and get a better response, right? So
Okay.
Advi, this side. Uh, Actually, the graph that you showed just before was pretty impressive because the drop that you showed.
Yeah.
Yeah. So this 5 megawatts, I know it's difficult in the industrial grade building to bring this drop. So you said we used two types of strategies here. One is the direct load control. The other one is the voluntary control. Voluntary control is of course a variable factor, and it might or might not work all the time.
Yeah.
So the most reliance would be on the direct control method. So
Yes.
in that we talked about various things on more of global temperature reset and variable frequency drives.
Yeah.
So which one came in handy, and how were these strategies picked up? As in, there might be temperature that is causing this. There might be external factors like the weather, the climate. You might also be interacting with the meteorological department to get the predictions on the weather also, and giving them information based on that. So which one came in more handy, and how were these factors picked up?
Right. So that one of the reasons why we were doing demand prediction, right, was to understand the effect of today's load on the potential curtailment that you would achieve, right? So and demand prediction includes weather-based model, the ARIMA model, not the ARIMA, the regression tree-based model was actually using forecasts from the meteorological office. In fact, USC campus had a weather station on campus, and we actually got data from that, right? So that got incorporated into the demand model, and the curtailment model gave you essentially a certain offset from the demand that you're going to have. From my recollection, duty cycling gives you the biggest instantaneous drop, right? Because if you've got 3 AC units in a building and you drop it down to 2, immediately you get a 1/3 shave, right, in the load that you have, right? So if you want instantaneous deep drops, duty cycling is good, but it also affects people the most because the 1/3 of the building that doesn't have the AC for an hour, right, is going to be affected. You're going to have some latent energy, right, cooling that's there. The variable frequency drive is much more sort of nuanced because there you can literally sort of change the RPM on a sort of 1 RPM granularity, right? So there the airflow will reduce. So that would give you more of a gradual shift in the usage. And global temperature reset again is similar to the variable frequency as well, from my recollection, right? So there again, but that is much more sensitive to the current ambient temperature.
So this variable frequency drive was, how will you will have to arrive at a complete model to identify where you have to drop the temperature and variate. So is it on its own a separate research that you did, or was it an algorithm that you did?
These were very coarse benchmarking that we did. We literally did experiments at, let's say, 3 or 4 different like speeds, right? Or for 3 or 4 different temperatures, right? So these were not very fine-grained models. These were coarse models done through experimental benchmarking, right?
So in these days, if you see, there are big buildings. For example, let's take the Singapore airport, the Changi airport. So all these places have two types of ways to utilize power. Also, one is a reusable energy, the other one is through the standard power that you get. So do we also is there also a possibility to cater these two and bring a decision on which power source can be used? I mean, can we do that take that as a problem? Is that possible?
Oh, definitely. In fact, one of the comments I had when I think talking about the USC campus was that there was no captive power within the campus, right? But many, especially in India, many of the industries do have some captive power, right? Every residential building has captive power through our DG sets and so on, right? That's again a very interesting dimension we didn't look at USC, but that was part of the broader scope within the smart power grid project, right? So, and that again gets into the incentive model, right? So, are your intensive incentives large enough for the industry to use their, let's say, DG set or other kinds of local resources, right? Because what you're effectively doing is that instead of you building a new power plant, right, you're essentially saying that I'll have a higher operational cost by maybe paying more than what someone pays for the operations of a DG, right? But I won't have to pay for the capital cost of a new power plant. Right? So that's the trade-off that you can make. And there again, that might be an incentive for even industries to, let's say, have a solar plant, right? Or a sort of wind plant. Right?
Yeah.
And
back
to
the
grid.
cost.
Exactly. Yeah. So you can actually make profit from the power grid through back to grid and net metering and so on as well.
So are there researches that are going on in this side also, as in to make decisions, because it is, as you say, it is not reliable. So there, it's not about the demand; it's more about the supply itself. And to make calls on when the supply is more and intimating the companies to use reusable energy, is that a possibility in the future? Are we looking at such things?
Right. Again, some of this work is dated, right? So I'm sure, but even back then, there was this discussion around how to do that, but at the utility scale as well, not just at the company scale, right? Because utility itself has multiple power sources, and some of these are actually costly ones. For example, they had a jet turbine that they had, which was literally sort of running what do you call a jet aircraft turbine, which would give you instantly, within a few seconds, you can turn it on, and you'll sort of get a few megawatts of power, right? But that's costly, right? One of the ways to think about this is that you leave the decision making to the industry or the campus, right? In terms of what is it that they would like to do, right, to achieve the target, and is the incentive good enough for that, right?
Okay, got it.
Right, so that's a way of federation, right? Because you don't want the utility to do fine grained control, and in fact, even from a liability perspective, the utility does not want to do that, right? Because tomorrow, if you sort of turn off some cooling, and that's for some kind of health center, and that causes some people to get into some health issues, right? The utility will be in liability.
Okay, thank you.
Sir,
Yes.
yeah, I would like to know if you used any simulation model for the entire solution which you deployed. So you had any simulation models before implementing the solution?
Right. No, for this project, we did not have any simulation model, because we don't work as much on the simulation space as probably we should. But that would definitely be a nice addition to this, right? So, for example, simulating the behavior of the HVAC system, right, would have been a much nicer, more reliable way to do it, rather than just using some very coarse data-driven models, right? So, though we didn't do it, that's definitely something that could be done.
So out of these applications which you presented today, so you had any simulation in any of these?
No, we unfortunately we don't do. My group does not do computational simulation. We do data-driven models, right? And that itself could sort of be simulated in a sense. You can do what if planning, right? So we, for example, for the curtailment strategies, we run a bunch of experiments. You could potentially call them simulations to see for different target curtailments, right? What is the mix of curtailment strategies that the system would give you, right? But that's a much more sort of very lightweight simulation compared to, let's say, simulating the behavior of a building as a whole, right? Or simulating the behavior of a HVAC system as a whole.
So do you use any tool? What tool do you use mostly? Is it a MATLAB programming or Python-based SymPy or something? What do you use? Just
like I said, we ourselves didn't use like numerical simulations for our projects, but any and all of these are valid ones. In fact, there are a dozen faculty in my department who work on such simulation models for various types of physical and natural systems at the CDS department. And they use anywhere from writing their own parallelized numerical solvers, to using MATLAB and R, to NumPy, SciPy, and then you have a bunch of these libraries out there. So anything that gets your job done would be my answer. Right?
Thanks. Yeah. Also, I had one more question. So these are nice engineering problems, if I'm not wrong. So I would also like to know what are the major areas of core theoretical research which is happening in IoT.
Sure. So again, some of these are the optimization problem that I talked about, right? That's a nice algorithm problem, right? So that's a bit of a theoretical problem. In this case, we simplified it to just a change-making problem. But when you start including constraints that I don't want to go to the same building again, right, for consecutive days, right? So there are a bunch of these, or you might put some social constraints saying that today there is going to be some VIP who's visiting the director's office, so I don't want to touch that building, right? So you can introduce a bunch of constraints, and the kinds of optimization problems that you can come up with that you want to solve theoretically are sort of literally unbounded, right? So this is one example of that. And even from the sort of system optimization perspective, right? So from the this particular problem over here again, a lot of it gets into designing scheduling algorithms, right? So that's adaptive, and some of these are even predictive algorithms, right? So this again gets into some of the I don't quite mean I don't know whether to call it a theoretical problem or an algorithmic problem, but it's definitely an algorithmic or a heuristic based problem that are going to be present.
Thank you, sir.
Sure. Other questions or comments before we move on to the next topic? Okay, so let's move on. So in the interest of time, so looks like I'm almost like at 60% speed of what I wanted to cover. I'm going to skip the next case study because there's some kind of similarity between this and what we just talked about. But I'll move on to the third case study. I'll share the slides with you guys offline, so you can always take a look at it. But let me talk about some of the low-cost air quality monitoring using Satvam, because this has much more complementary ideas compared to what we just talked about from smart power grids at Los Angeles, right? And this is a project that we are doing currently with IIT Kanpur, IIT Bombay, and also Duke University in the US as part of an Indo-US Science and Technology Forum project. And the project is led by Sachi Tripathi at IIT Kanpur, who's actually part of the National Air Quality Mission of India. And the idea behind this project is to try and use IoT technologies to get a better handle on air pollution within India. Right? Before COVID hit us, air pollution was probably one of the biggest news grabbing headlines, right? So when it comes to sort of the impact on health and impact on monuments and so on, right? So in fact, there have been studies recently that say that air pollution has a whole body effect. It doesn't just affect your lungs, but it literally affects your entire body, many of the organs in your body, right? And it sort of reduces the life expectancy and so on substantially. So it has effect also on sort of historical structures, like Taj Mahal getting yellow is in the news once in a while. But it also has economic impact, right? So air pollution affects things like solar power generation, right? Because if it's going to be polluted, the efficiency of a solar panel sort of drops down because there's lower sunlight, and that it also causes, let's say, dust to coat your solar panels, which also drops their efficiency. And the impact on health and healthcare also has an effect on the economy as a whole, right? So be it, for example, burning of crops in Punjab that causes, let's say, smoke and pollution in Delhi and so on. So it's a very interconnected problem. It's not just a simple problem that you can solve, right? And this also has to do with industries generating sort of toxic fumes and how much of it can be sort of cleaned other industry or using better technologies and so on. So there's a health, economic, sort of heritage, all kinds of impact of air pollution, right? And again, you would have seen many different reports on the impact of such sort of air pollution, right? Now, given this, the goal of this project was to see if we can use affordable, low-cost technologies, IoT-based technologies, at large scales in order to have a better information-driven approach to air quality monitoring and eventually policy making, right, to improve the air quality, right? And one of the sort of motivation for this particular project came from the sort of infamous odd even sort of vehicle routing strategy in Delhi, right, about 4 years back, where, if you recollect, there was a rule that said that on certain days only vehicles with an odd registration number could be on the road, and on other days only those with an even registration place could be on the road, right? So one of the interesting aspects over there is what was the impact of this strategy, right? Or did it really help reduce pollution or not, right? But in the process of actually trying to figure out, and this is various studies done by sort of domain researchers who work on air pollution, including Tripathi at IIT Kanpur, they wanted to sort of first of all collect data, right? Saying that, okay, let's look at the data for these different days, right? And one of the observations that they had was that where is the data available from, right? So there are two types of sensors that were available, right? So one was these uh, costly reference plate monitors operated by the Central Pollution Control Board, right? Every city, state has their PCBs, right? Pollution Control Boards, and these are supposed to be having one or a few air quality monitoring stations within the city, right? A large city might have maybe 10 of these, right? And these are high-end monitoring stations that cost maybe 1 or 2 crores of rupees, right? And these give scientifically highly accurate data points, right, of multiple sort of sensor observations. It could be particulate matter, PM 2.5, PM 10, and so on. It could be gases such as ozone and nitrous oxide and sulfur dioxide and so on, right? So they give you a variety of parameters with a high accuracy, but there are only maybe a few or a dozen within a city, right? In fact, in Delhi, there were about 15 or so back then in the airport and in the US mission and so on. But what they observed was that even despite just having a dozen of them, not all of them were operating, right? So for a couple of months period, right, they actually saw that many of these were completely offline because people are not maintaining it, and for some they were online only part of the time, right? So despite having spent crores of rupees, right, in installing these, right, not all of them were working 24/7, right? So when it came to actually going and doing an analysis, the data was not there, right? On the other hand, they also looked at data from a crowdsourced project launched by an NGO, right? I think it was called indiaspend.org or something, right? Where they had actually sort of given specifications for these IoT devices, which people could just buy off the internet, assemble it together as a DIY project, right? And they could sort of transmit that data to some centralized sort of crowdsourced server, which anyone can look at and download and so on. And they actually found that you had way more sort of continuous data collected from these crowdsourced devices, right? So in Delhi, compared to these the high-end sensors, right? And this was actually one of the sort of key motivators, right, for this particular project, where the idea was that instead of having a few highly accurate sensors, right, even if it were up 24/7, right, can you have potentially tens or hundreds of low-cost sensors spread right across the city and collecting data 24/7, right? And would that sort of be helpful to get a better view of what happens within the city from a pollution perspective, right? And again, these could complement each other. It's not like you want to replace all these high-end sensors with the low-end ones, but can you sort of get more information through them, right? So this Sattvam project, like I said, it's a collaboration between 4 different universities, and it looks at the entire end-to-end spectrum of the IoT pipeline, right? So this is designed as an IoT project, right? So all the way from low-cost sensing and sense making, right? And a key aspect of this project is like actually calibration of these low-cost sensors, which I'll talk about in more detail. It also gets into things like doing energy harvesting. Can you use things like concentrator panels or solar panels alongside the sensor boxes so that you don't have to have power supply from the city utility, or if there's a temporary power outage, you can still keep collecting data, right? We also looked at sort of low power ad hoc wireless sensor networks, and we also looked at analytics on the edge and cloud, right? So there are different teams looking at different aspects of this problem, right? It's very inherently interdisciplinary in nature, right? And this is how the overall architecture looks like, right? So you have your air quality sensors, and the sensors themselves, we just bought it off the shelf. And we essentially are looking at using these wireless modes, right? These are sort of Zolosia modes that we purchased off the shelf as well. And these connect with each other through a 6-LoWPAN network. And these send data to a gateway device, which happens to be a Raspberry Pi device, right? So many of these edge devices with co-located sensors use an embedded platform and wireless sensor networks to send the data to a gateway device. And in the gateway device, you sort of collect the data, do potentially some basic resiliency and data analysis, and you send the data to the cloud. And from the cloud, you can do various kinds of analysis on top of this data, do visualization and so on.